Okay, welcome back to MATH2. In this lesson, we're going to look at matrices in the linear algebra part, and we're going to look at regular expressions in the languages part. I hope everybody managed to make the exercises. If not, please feel free to join me in a meeting. Okay, let's look at matrices. A lot of this stuff will be known to you already. And so if we look at a matrix, in fact, it is always something like a number of rows and a number of columns. And we can have matrices of several sizes. So this one is a 2 by 2 matrix. It has 2 rows and it has 2 columns. We can have 3 by 2, 4 by 7, whatever size you like, you can have a matrix of it. If we have two matrices, we can do some operations on them. For instance, we can add two matrices. So if we would add x plus y, it is quite straightforward. You just look for the similar positions. So in this case, we have 2 and 4 on the same position. So 2 plus 4 becomes 6. We have minus 1 and 3 at the same position. That will give us 2. We have 3 plus 2 in the same position. That'll give us 5, and 1 and minus 1 in the same position. That'll give us. Okay, so x plus y becomes this result matrix. If we look at x minus y, it's exactly the same situation. So we just do 2 minus 4 becomes minus 2, minus 1 minus 3 minus 4, 3 minus 2 is 1, and 1 minus minus 1 would become 2. So this one will give that result. We can also have a scalar multiplication. So then we first apply the scalar multiplication to the matrix. So this would become 4 minus 2, 6 at 2, plus scalar multiplication with y, 12, 9, 6, minus 3. And then, of course, we just need to add them again. We can also multiply matrices, and then hopefully you still remember that to multiply a matrix, you get an answer on a specific spot by multiplying a specific row and a specific column. So for instance, if we would like to get the answer at this position, then we would have the first row with the first column. So that would give us 2 times 4 minus 1 times 2. So on this position, it would give us 2 times 4 minus 1 times 2. For this position, we would have the first row and the second column. So that would give us 2 times 3 minus 1 minus 1, so that would be 1. For this position, we would use the second row and the first column, so that would give us 12, 3 times 4, plus 1 times 2. And for this position, we have left 3 times 3, that would be 9, plus 1 minus 1, 1 times minus 1 would give us minus 1. So the total result would be 6, 7, 14, and 8. So if we have another example, let's try to calculate this result. So to multiply these two matrices, that would give us for the first spot, the first row, first column, that would be 2 times 2, 4, plus 3 times minus 1, so minus 3. For this spot, we would get first row, second column. So that would be 2 times minus 3 would be minus 6, plus 3 times 2 would be 6. And for this one here, we have second row, first column would be 2. So 1 times 2 plus 2 times minus 1 would give us minus 2. And this position here would give us minus 3 plus 4. And if we calculate this one, that will give us 1, 0, 0, 1. This result is called the unity matrix. So with only on this diagonal from left up to right down only ones and all the other spots are 0 is called the unity matrix. And with this matrix, if we get this as a result from a multiplication, then we say that these two matrices are each inverse matrix. And so if we look at this on this sheet, so the unity matrix is the one given with 1, 1 on the left diagonal, and the two matrices which give this result are called inverse matrices. So B is the inverse matrix of A, and we write this as A minus 1, A minus 1. Another specific of a matrix is called the determinant. And the determinant, if we look at a matrix, is just by using one diagonal and subtracting the other diagonal. So the determinant of this 2 by 2 matrix is denoted by A times D minus C times B. So it's just a number. And we will write this number, we can denote it by using those lines around the matrix. So if we would do this, then the determinant of this one would be A times D minus B times C, which is just a number. We can only calculate the determinant for square matrices, and for this program, the linear algebra part in MATH2, we will restrict ourselves to 2 by 2 matrices. So a very simple determinant. So if we have this determinant, we can use the determinant to calculate the inverse matrix. And that's just a small trick. So if we have a matrix ACBD, like we see on this slide here, then the inverse matrix is given by determining the determinant, calculating the determinant, and then the inverse matrix would be 1 divided by the determinant, and then we have a strange thing here. We switch the elements on the left diagonal, and we leave the elements on the right diagonal, and just put a minus in front of them. So let's see if this is really true. So if we look at the action here, and we would calculate A, B, C, C, D times and multiply with 1 divided by the determinant A times D minus B minus C A, then this should result in 1, 0, 0, 1. Please check this out yourself. As one extra remark, if you see on the slide, if the determinant doesn't exist, then of course you cannot calculate the inverse matrix because we're not allowed to divide by 0, because then this thing here would become 0. So then we cannot calculate an inverse matrix. So let's try this one. What is the inverse of 3, 2, 1, 2? Okay, let's first try to calculate the determinant. So the determinant of this matrix would be 3 times 2 minus C times B, so 2 times 1. So that would be 6 minus 2 would be 4. So the inverse matrix of this one would be 1 divided by 4, and then we switch the elements on the left diagonal, so this would become 2, this one would become 3. We leave the ones which are here and we just put a minus in front of it. Okay. So apparently this matrix is the inverse of that one. So let's try to check this. So if we multiply those two matrices, we have 1 divided by 4 times, okay, 3 times 2 would be 6, plus 1 times minus 2 would be minus 2. On this position here, we have 2 times 2 minus 2 times plus 2 times minus 2, so that would give us 0. On this position, we have 3 times minus 1 plus 1 times 3, gives 0 again. And on this position, we have 2 times minus 1, minus 2, plus 2 times 3 would be 6. So the result would be 1 divided by 4 times 4, 0, 0, 4. And indeed, this will give us the unity matrix. So we have shown that 1 divided by 4 times this matrix is indeed the inverse matrix of 3, 2, 1, 2. Okay, let's try this yourself. So can you give me the inverse matrix of 1, 3, 5, 2? So let's first calculate the determinant. And that would be 1 times 2 minus 3 times 5. So that would give us minus 13. The inverse matrix itself would be 1 divided by minus 13. Then switch these two. So the left diagonal, leave the other ones and put a minus in front of them. Okay, that's quite simple. So just to make sure that it really works, multiply this one again with your original matrix and see if you can. Okay, one last exercise just to get a hang of it. So the determinant of this one would be 6 times 2 minus 4 times 3. Ah, that's a pity. Now we get 0. So apparently this matrix does not have an inverse matrix. Okay, how can we use this determinant thing with the equations we've looked at in the previous lesson? So let's look at these two equations. So we have something times x, something times y equals something, and a second equation. And maybe you recognize something like a matrix in it. If we put the stuff in front of the x and in front of the y together, so we would have 1 minus 3, 2 minus 5, we can look at these numbers as a sort of a matrix. And if we then multiply this one with x, y, it's amazing, but then we get 1 times x plus 2 times y minus 3 times x minus 5 times y. So that is exactly the left part of those two equations. So apparently this matrix would be the same as 3, 2. So now we have made a new representation of two equations, and it is called